Okay, Assalamualaikum dan selamat sejahtera. So now I will continue my lecture for topic 1 for part 2. Okay, this is the outline for chapter 1. And I already covered 1.1 and 1.2 in part 1. So I will continue for 1.3, 1.4 and 1.5 for part 2. Okay? Okay, next we go to 1.3, classification of distribution system. Okay, the distribution system may be classified in the following ways. Okay, there are 4 items for classification. The first one is according to nature of construction, and the second one is according to nature of current. The third is according to number of wires, and fourth is according to the scheme of connection. Okay, for the first one according to nature, we have to consider the first is overhead distribution system, A, and also the underground distribution system. So we have to consider 2 types of construction, which is overhead and also underground. Okay, the second part is according to nature of current. So there are 2 types of current, which are DC current and also AC current. And third one is according to number of wire. Okay, as we know, we have 2 types of power system for distribution, which single phase and 3 phase. That's why there are 2 types of wire. The first one is 2 wire, and the second one is 3 phase 3 wire. Okay, this one is for single phase. Okay, this one single phase 2 wire, and this one is for 3 phase 4 wire. Okay, and the fourth one is the according to the scheme of connection. There are 3 types. The first one is radial system, the second one is ring system, and the third one is interconnected system. Okay, and then we go to primary distribution lines for feeders. Okay, this one is the primary side. Okay. Okay, the 3 step down to 11 kV secondary substation is established where the load requirement for the transformer is 5 MVA. Okay, this one is for TNB side. So the incoming for secondary from the secondary substation and incoming for the primary distribution is 11 kV. Okay, and then when the load requirement increase and cross about 8 MVA, okay, the losses in 3 kV sub-transmission line become large. Okay, when the power is increased, the losses also increase. Okay. Okay, the number of primary substation, distribution lines emanating from 6 to 11 kV secondary substation is 6 to 10. Okay, means that the ratio for the step down is equal to 6 kV to 11 kV. Okay, still for the primary feeders. Okay, there are 3 types. Okay, the first one is radial, and second one is loop, and the third one is ring. First, we go to the radial primary circuit. Okay, this one is the radial. This one you already learned in utilization. Okay, there are 3 types. This one is radial. Radial, as we know, it is similar like series. Alright, so there are substation here and going to circuit 1, circuit 2 and circuit 3. The circuit 1 may be to connection for factory, circuit 2 feeding substation in the city, and the third one is for rural areas. Okay. Okay, this is the advantage and disadvantages or limitation of the radial feeders. Okay, the first one is advantages of radial. Okay, for radial, there are a heavy load very near the secondary substation. Okay, and isolated loads. and then an area of low load density such as a village. So we can see here the advantages for radio system is the system is isolated loads. Means that for each types of load, for residential, commercial, industry, the load are isolated. Okay, there are no interconnected from each load. And then this is the limitation of the radials. Okay, the first one is when the load demand on the radial feeders increase, the length of the feeder has to be extended. Okay, this result in a greater voltage drop, which may cause the voltage towards the tail end to reach a value below the permissible limit. So means that if you want to increase the load, you have to extend the feeders, the length of the feeders, so that when the length of the feeders is increased, the voltage drop also increase. Okay, for voltage drop, you have learned in utilization for chapter 4, I think. Okay, and then second one is when a fault occur at any point along the length of the feeder, supply to all consumer beyond this point towards the tail end get interrupts. Okay, next we go to the loop primary circuit. Okay, this one is the circuit for loop primary. Okay, to overcome the limitation of the radial feeders, the loop primary circuit is taken to use. Okay, we can see here, there are one substation, secondary substation, can outgoing. From the secondary substation, there are two outgoing here. The first one is to distribution substation 2, and then distribution substation 3, and also outgoing to distribution substation 1. Okay, this is, the connection is in loop for 3 distribution substation. The supply is 11 kV for each distribution load. Okay, when fault occur at A, here, we can see that CB is for circuit breaker. So when fault happen at A, point A, so circuit breaker 6 and circuit breaker 1 will be open. Means that there are no supply connect here. So that distribution substation 2 will get the supply from the secondary, from circuit breaker 4 and 3. And distribution substation 1 still get the supply from the interconnection between CB3 and CB2. Even here is isolated. Okay, because of fault. So substation 3 also get the supply from the secondary substation, from the connection between circuit breaker 5. So means that any fault happen across the line, the supply the distribution substation still get the supply. Okay, next. Okay, this is the explanation for what I have explained before. So you can just read. Okay. Okay, this system is generally used in towns and city. Okay. The reliability of the supply in the system has improved in comparison with that in the radial system, as it has an alternative supply. Okay. Because there are two incoming supply from the substation. Okay, however, it must be realized that the source of supply for the whole loop system is a single secondary substation. Means that the supply is incoming from the one or single secondary substation only. So if a fault occurs in the secondary substation, causing a failure of the 11 kV supply source to the whole of the system, means that is the secondary or the source of the supply is fault. So means that the other 3 distribution substation will not get the supply because there are no backup for any substation. Okay, next we go to ring, main or network system. Okay, this is the last type, the final types. Okay, we can see here, this is the improvement from the ring. Okay, from the previous, from the loop. Okay, we can see here, there are two secondary subsection, A and secondary subsection B. So the difference between the ringman and the loop is, for ringman, there are two incoming subsection. Okay, but for loop, there are only one secondary subsection. Okay, that is the difference. So we can see here, for this subsection, for this condition, distribution subsection 2, 1 and 3 will get the supply from the subsection A and B. So any fault occur for subsection A or B, distribution subsection 1, 2 and 3 still get the supply from other subsection, either from subsection A or subsection B. Okay. Okay, this is the explanation for ring system. Okay, I already explained previous slide. Okay, here the ringman system is by far the most reliable for continuity of supply. It gives a better voltage regulation and less feeder losses. Because there are two backup, right? Because from subsection A and also from subsection B. Okay, circuit breaker are used instead of fuse for protecting the transformer in ringman system due to heavier loads. Okay, distribution subsection are a link between feeder and distributors. Okay, so this one we go to the secondary distribution. Okay, this one is for distributor. Okay, as we know, the system for primary and secondary is almost the same types. We have radial, we have loops, and also we have ring. But the incoming voltage and outgoing voltage is different. Okay. Okay, usually for primary, we have incoming 33 kV and outgoing is 11 kV. But for secondary distribution, the incoming feeders is 11 kV and step down to 415. Okay, this one is for distribution substation, right? Okay. Okay, a consumer at a near end of the distribution substation may have a voltage as high as 436 volt for three-phase, or we know as, in Malaysia there are 415. Okay, and for single phase is 240 for single phase during light load hours. Alright. Okay, and then the circuit for the secondary distribution system are essentially the same as those for primary distribution, except that they are on a smaller scale. So it means that the design is same, the system is same, but the value is smaller for distributor part. Okay, this is the type. You can see that for secondary part also same as primary. So we have radial, loop, and network. Okay, this is the design for radial. Okay, as we can see here, 11 kV incoming. Okay, step down to 415. And then, going to LV circuit breaker. And then go to the load. Okay. Okay, this one is the expanded radial scheme. Okay, still we have one source here. And then radial. This one is radial 1. Okay, this one is radial 2. And also this one is radial 3. Okay, this is the loop system for distributor. Okay, in this case, the reliability of supply is better than in the radial system. In the case of fault on one line, the load can be fed from the other by connecting switch S. Okay, by connecting switch S, the load can be fed from others. So, from this one and also from this one. Okay, however, a fault in the 11 feeder will cause the interruption. Okay, this one. Of supply to all consumer. Okay, so that circuit breaker and the fuse, this one is circuit breaker and this one is fuse, unit provide a protection for the transformer and line respectively. Okay, this is primary selective scheme for loop system. Okay, next is banked secondary system for distributor. Okay, when radial secondary circuit are supplied by a single transformer, high starting current of motors may cause objectionable voltage drop. One of the most effective and economical means of controlling such a voltage drop is the banking of distribution transformer. So this one is the incoming, okay, 11 kV primary distribution, and this one is the secondary. Okay, this secondary is connected with transformer 1, 2 and 3. Okay, transformer are said to be banked when two or more supply from the same primary circuit are parallel to feed into the same secondary mains. Okay, by this arrangement, more than one path is provided over which high currents can flow. This results in lowering the extent to which the voltage fluctuates on the line. Okay, further advantage of this system, the first one is more reliable. Okay, have alternative supply from other transformers. Okay, and then have better load distribution for each transformers. And then the voltage drop in the system is reduced. Okay. The system is mostly used in the area of low load densities when a multiple primary and secondary network is just justified. Okay, if a fault occurs within one of the transformer, it will be automatically disconnected from the line by blowing the two secondary line fuse and primary transformer fuse without interrupting service to other consumers. Okay, this is the secondary selective scheme. Okay, for banked system, there are two transformers here. You can see connecting to the load. Okay, this is the sparing transformer scheme. Okay, we can see here there are 4 transformers. 1, 2, 3, 4. Okay, this transformer is for spare. Okay, this one is 1, 2, 3 is in operation. Okay, next we go to subtopic 1.4, load data. Okay, first, typical range of industrial load. Okay, there are 2 types. The first one is light industry. Okay, the characteristics is for 50 kVA up to 7,000 kVA. Okay, for heavy industry, the load is 1,000 kVA to 200,000 kVA. Okay, typical industrial load. There are HVAC, and then we have process equipment, pump, compressor, and fans. Okay, and then industrial service such as boiler, water treatment, and then for workshop and laboratory equipment, and also motor control center. Okay, this is the type for industrial load. Okay, initial maximum demand estimation. Okay, we have to know what is the maximum demand for that industrial to make sure that the voltage supply is enough. Okay, there are 2 methods to estimate the maximum power demand in visibility/conceptual design stage. This first one is VA/M squared or watt per feet square. Okay, this is normally applied to commercial building where the typical load are lightings, general power, and HVAC. Okay, for example, 50 to 100 VA per M squared for non-retail buildings. Okay, 60 to 150 VA per meter square for retail buildings, 0.9 watt per feet square for lightings, and 4.7 watt per feet square for air condition. Okay, this one is the standard, okay, commercial building. Okay, because we can see here, the loads only lightings, power socket, and HVA AC. Okay, then second one is maximum demand for a similar building for industry. Okay, applicable for residential, commercial, and industrial building. Okay, for example, plant A having maximum demand of 2 MVA, then this figure can be used for plant of similar capacity. Okay, usually for maximum of a similar building, this is most likely for commercial building. Okay, next is the initial maximum demand estimation. When some or all of the load characteristics are not known, the value shown below may be used to give a very appropriate estimate for VA demands. Okay, this is based on Electrical Installation Guide 2016 Schneider. Okay, we can see here for pumping station compressed air, the estimation is 3 to 6 VA per m squared. Okay, for ventilation of premise, 23. For electrical convection heaters, private houses, flats and apartments, the total VA per m squared is 115 to 146. Okay, for flat is 90. Office, 25. Okay, dispatching workshop, 50. Assembly workshop, 70. Machine shop, 300. Painting shop, 350. And heat treatment plant is almost 700 VA per m squared. Okay, this is the estimation of the load characteristic. Okay, next is detailed load estimation. Okay, it can be calculated either in kVA or amps. Okay, if the output is given in kW, the kVA can be obtained using formula. Okay, to get the kVA, kVA is S, right? Apparent power. So it's equal to kilowatt. This one is real power divided by power factor times with N. Okay, this one is the factor. Okay, future load should be considered as given in spare circuit for future use. For better load estimation, a proper utilization factor and diversity factor should be considered, as not all equipment or load operate simultaneously. Okay, next we go to utilization factor. What is KU? Okay, in normal operating conditions, the power consumption of a load is sometimes less than that indicated as its normal power rating. A fairly common occurrence that justifies the application of utilization factor in the estimation of realistic values. Okay, this factor must be applied to each individual load with particular attention to electric motors, which are very rarely operate at full load. Okay, in an industrial installation, this factor may be estimated as an average of at 0.75 for autos. Okay, diversity factor, KS. Okay, the definition of diversity factor is, okay, KS is equal to diversity factor is equal to maximum demand divided by connected load. Okay, this one is based on IEC defined as coincidence factor. Okay, typical diversity factor value, okay, for lighting loads is 100%. Okay, general purpose power circuit socket 50% to 40% to 50% for industrial installation. Okay, and then main switchboard 80% to 90%. Intermittent duty loads is less than 50%. Okay, this is the example for maximum loading for MCC. Okay, you can see here there are load description here, cooling tower, okay, and then the cooling tower, 2 fan, and the heater, and then have fan coil, water pump, extract fan, compressor, future pump. So all the total connected load is 42 kVA. Okay, this one is for 3-phase. Okay, and then we have single phase load, which cover only fan coil. So the total connected load is 2.2. And then we have single phase for Y, only for extract fan. Okay, there are 1.3. So 1.3 total load. And then for blue phase, okay, this one, single phase for blue phase, only connected to the compressor. 1.6. So the total is 1.6. So the yellow one is, okay, this is the total connected load to that industry. Okay, total load on the MCC is 47.1 kVA. This is the total in the yellow one. Okay, this example for maximum loading for LV switch board. So we have DB1, DB2, MCC1, MCC2. Okay, this is the kVA, the total load. Okay, and then we have packaging machine. Okay, connected load. This one is kilowatt. And then operating. Okay, and then this is the K, the factor. And this is the kVA. Okay, CO2 compressor. Okay, this is the kVA. Okay, and then water pump 1. This is the kVA. Okay, and then water pump 2. Okay, there are no kVA here because this is not in duty. This is spare. Okay, and then welder. Okay, and then the connected load is 36. Okay, the total 50. This one 50 for future, for spare, planning for future. So total load on LV switchboard is 461.1 kVA. Okay, this one is maybe based on the estimation. Okay, before we do the actual design. Okay, next we go to diversity factor, KS. Okay, rated diversity factor for distribution switchboard. Okay, the assumed loading of the outgoing circuit of the assembly or group of outgoing circuit may be based on the value. Okay, for distribution, okay, this is the type of load. Okay, distribution for 2 and 3 circuit. Okay, the factor, diversity factor is 0.9. Okay, 4 and 5 circuit, the diversity factor is 0.8. 6 to 9 circuit, 0.7. 10 or more, 0.6. Okay, electric actuator, 0.2. And motor less than 100 kilowatt, 0.8. Motor more than 1 kilowatt is 1. Okay, this one is the diversity factor according to the circuit function. Okay, lighting, the KS is 1. Heating and air is 1. And socket, 0.1 to 0.2. Okay, and this one is for lift. Okay, for motor. Okay, 1, 0.75, 0.6. Okay, in certain cases, notably in industrial installation, this factor can be higher. The current to take into consideration is equal to nominal current of the motor. Okay, this is the example of application of factor KU and KS. Okay, utilization factor and also diversity factor. Okay, this is, we can see here, this is 3 load. Okay, commercial load, workshop A, workshop B, and workshop C with different types of load here. Okay, and then this is the kVA for each load. Okay, we can see here. Okay, this one is the utilization factor in the box here. Utilization factor. Okay, the first one, to get the apparent power demand, okay, maximum kVA, we have to times apparent power, this apparent power with utilization factor. So we get the apparent power. So we have to calculate all loads, okay, this one, to get the apparent power demand in maximum. So next we go to level 1. Okay, this one for distribution box. Okay, this is the diversity factor for each load. So different loads have different diversity factor. Okay, we can see here, this one is for 0.75, this one is 0.2, 1. Okay, this one based on the previous table that I have explained before. Okay. Okay, so to get the apparent power demand, okay, we have to times diversity factor with the apparent power demand maximum. So this part factor, we have to times with apparent power. So then we get the total power. So this 14.4 is based on the total power that connect to 0.75 diversity factor. Okay, same goes to other loads. So for 5 socket here, 5 sockets, okay, we have to times 18 with 0.2. So we get the power demand is 3.6. So we have to calculate for all load. Okay, that is for level 1. So next we go to level 2. Okay, this one is for workshop distribution box. Okay, this one for each load. Because different load have their different diversity factor, right? Okay, this one is for total workshop A. So the diversity factor for each industrial is 0.9. So we can see here 0.9 for A, for B also 0.9, for C also 0.9. So we have to times all the power from the workshop load with 0.9 to get the apparent power demand for the whole workshop. Okay, this one. So means that 0.9 times with total this one. So this one total. So we get 18.9. So same goes to workshop B. This one 15.6 is based on 0.9 diversity factor times with all the connected load. Okay, same goes to workshop C, 0.9 times with all the connected load here. Okay, so okay, this one is the for each types of workshop. Okay, then for level 3, this one for this level is the main general distribution board. Okay, this one is for connected to TMB side. Okay, that's why the diversity factor is also 0.9, but we have to time with all the total connected load for workshop A, B, and C. So the total load here is 72.3. So we have time to 0.9. We get 65. So this is the total load apparent power that will connect to secondary side of transformer for LV side. Okay, clear? Okay, this is the old supply scheme for various maximum demand. Okay, we can see here, okay, there are some range of the load and the types of the scheme. Okay, up to 12 kVA. Okay, this one is single. We use single phase 240. And the typical supply scheme is only overhead service from LV mains. Okay, this one, as we can see that for residential always use overhead cable. Okay, and this is for single phase. And then for load 12 kVA to 100 kVA, this one. Okay, the supply voltage is 3-phase 415, and the typical supply scheme is 3-phase overhead or underground cable. Okay, and then for 100 kVA to 1000 kVA, the supply voltage is 415. Okay, and then the connection is direct cable service from LV board from a substation. Okay, we use direct from every board because the load is higher. So for load 1000 kVA to 5000 kVA, okay, the supply is 11 kV. Okay, direct fed from TMB 11 kV switching station. So for this load, just directly fed from the TMB. Okay. Okay, and then for 1000 kVA up to 10,000 kVA. Okay, to 2 kV, also direct fed from TMB to 2 kV. And then 5,000 kVA up to 25,000 kVA. Okay, we connect with supply of 33 kV. Also direct fed from TMB 33 kV. Okay, and then above 25,000, okay, this one is for transmission, right? Rated, okay, 132.275, this one is from generation to transmission. So also direct fed through TMB supply 132 kV and 275 kV. Okay, this one is the new one. Okay, we can see here for new one. Okay, there are, okay, the 4 atom here. Okay, okay, the rated also different. This one is for new scheme. Okay, and then the supply voltage here also different. Okay, okay, the revision is made for the range of the kVA and also the voltage. Okay. Okay, we can see here. The voltage for single phase is 230. Previously, the voltage is 215. Okay, and then the voltage for 3 phase is 400. And the old one is 415. Sorry, for single phase is 220. Okay, 240, sorry. Okay, this one is, for old one is 415 and the new one is 400 volt. Okay, this one also 400 volt. The old one is 415 and this one also 415 for old. Okay, this is the common connection for transformer. Okay, we can see here L1, L2, L3 is for represent as live connection. So red, yellow, blue. Okay. Okay, this is the transformer for primary side. You can see here for primary side is in delta connection. And for secondary side, this one is in star connection. Okay, this one is going to the load. Okay, live, neutral. Okay, why delta grounded star? Okay, delta at primary and star at secondary. Okay, why delta at primary? Okay, free of third harmony of the magnetizing current and any Polish homopolar current are free to circulate through the side of the delta without flowing into the network. Thus, the magnitude flux remains sinusoidal at the secondary. Okay, in case of unbalanced load at the secondary winding, okay, the secondary part, the reaction current observed by the primary flows only through the corresponding winding as shown in figure without affecting the other two. Okay, grounded star at secondary. Okay, why happen? To make line and phase voltage easily available. For safety reason, since in the event of the fault between MV and LV side, the voltage at the secondary remain close to the phase value, thus guaranteeing higher safety for people and maintaining the insulation. Okay, this is the basic installation of industrial plant. Okay, we can see here from transmission line. Okay, and then going to step down transformer. Okay, transformer we have primary side. This one is secondary side. And then going into the load. What? This one connected to the load. Okay, the MV line of the utility company. Okay, this one is MV protection device of the utility company. And then take up point of the user in the delivery room. And then go to MV connection cable from the delivery room to the user room. And then there are protection device here. And then we have transformer for MV to LV. This one for step down the voltage. And this is the load. Okay, we have LV bus bar and then connect to each load. Okay, this is the method of transformer installation. The first one is a substation with a single transformer. Okay, this one, you can see, only single transformer. So, one transformer connect to all loads. Okay, in the case where the protection device also carries out switching and isolation functions, an interlock must be provided which allows access to the transformer only when the power supply line of the substation has been isolated. Isolation of the SMV switching. This one is for switching and isolation device positioned immediately to supply side of the transformer. Okay, this one is for incoming from transmission. And this one is transformer to step down the voltage and then going to the load. Okay, this is all the load. Okay, method 2, substation with 2 transformers with one as a separate for the others. Okay, this one is from transmission. Okay, we have 2 transformer. Okay, and then from 2 transformer going to load. Means that this load L1, L2, L3 share 2 supply from transformer 1 and transformer 2. Okay, this circuit breaker, okay, this is the explanation. Okay, the circuit breaker on the LV side must be connected with interlock. Okay, this one is interlock. Okay, so from the secondary side must connect to interlock. This one is interlock, yeah. It's interlock. Okay, function is to prevent the transformer from operating in parallel. Means that the transformer cannot be operating in parallel. Only one transformer can operate in one time. So, this interlock will be used to make sure which transformer is operate at one time. Okay, apart from the switching and isolation device of the incoming MV line, it is advisable to provide a switching, isolation and protection device on the individual MV riser of the 2 transformer. Okay, this one. Okay, IMV1, this one for IMV2. So this is the individual protection device for each transformer. Okay, next we go to method 3. Okay, substation with 2 transformers. Okay, still use 2 transformers which operate in parallel on the same bus bar. Okay, means that the both transformer operate synchronized. Okay, this one, transformer 1 and transformer 2. Okay, possible to use 2 transformer with lower rated power. Okay, operation in parallel of the transformer could cause greater problems in management of the network. And when coordinating the protections, the fact that the overcurrent of the LV side is divided between the 2 transformers must be taken into considerations. So means that this load, okay, share the energy from the transformer 1 and transformer 2 with lower rated power. Okay, next, the last method, method 4, is substation with 2 transformers which operate simultaneously on 2 separate half bus bar. Okay, this one still 2 transformer, but here there are interlock here, and also we have bus tie. This one. Okay, providing a CLV, bus tie and interlock, which prevent the bus tie from being closed when both the incoming circuit breaker from the transformer are closed. Okay, this management method allows a lower value of the short circuit current on the bus bar. Okay, next. Okay, last subtopic 1.5 is transformer sizing. Okay, transformer sizing is generally based on first total maximum demand. Okay, this one is based on the total maximum demand of individual or group consumer. Okay, and then installed voltage level based on the kV, and also must be based on the method of installation or arrangement, and then also the short circuit capacity here. And then the criteria to be met here, the first one is voltage drop of secondary transformer must be less than 10%. Okay, the punya voltage drop must be less than 10%. And then motor full load current is less than or same with 65% of transformer full load current. And if motor start more than once per hour, transformer size should be increased additionally 20%. Okay, because there are more than one, so the current for the starting current is higher. That's why the transformer size should be add for another 20%. Okay, that's all for topic 1, part 2. And I will continue to explain for calculation in part 3. Okay, that's all. Thank you.